Okay, we're going to go over some of the finer points on this PowerPoint presentation, okay? Just maybe reiterating some of the things, okay? We've talked about, okay, so we'll start it from here and talk about, of course, the conversion from rectangular to polar or polar rectangle. You know, we take a point in polar, which is r theta, okay? And then we superimpose our x and y axes on there. And we know that we can, through the simple right triangle relationships, cosine equaling x over r, so therefore x is equal to r cosine. The sine is equal to y over r, so y is equal to r sine. That's a set of conversion formulas in going from polar to rectangular. And then the other way around, we can see that Pythagoras, of course, would tell us x squared plus y squared equals r squared. And then, of course, we know that the tangent of theta is y over x. So therefore, theta is the inverse tan of y over x, which allows us to do our conversion the other way around from polar to rectangular, okay? Some issues on the calculator if you want to use, okay? You go to the mode and you go to set it to polar, okay? The theta is the angle of rotation. Typically, you want to drive that up to 2 pi, okay? Of course, you can always alter that, okay? And then the increments are usually, that's your call. I think we're going to do, you know, you could do the pi over 12 if you want it, okay, or the which will put you every 15 degrees, okay. And then once you go into the graphing mode, you can just put in your just put in the function you want to graph, okay. And we've looked at that numerous times over, okay. If we wanted to convert that over to our rectangular coordinates, we saw that we could effectively take that starting equation and multiply both sides by r, and then recognize that we have r cosine of theta in here, which is the x value, and r squared is x squared plus y squared. Okay, so those things are going to be replaced, and in doing so, we can recognize, hopefully at this point we have a circle, and we can pull over and complete the square to identify the center and the radius of that circle, as we see right here, okay? A polar equation of a line, as we can see here, we certainly know that that's a line easy enough to graph, and with simple substitution by those properties that we saw earlier, x equaling r cosine, y equals r sine, put those in, and the expression turns into, as we see here, okay, 2r cosine plus 3r sine equals 6. We're going to factor out r, and then we're going to solve that for r. And of course, this is the circle. I mean, this is, sorry, this is the equation of a line in polar, and there it is graphed for us, okay? And as you can see, they're one and the same lines, okay? Awkward looking equation of sorts, okay? But nonetheless, it is the equation of a line in polar. Not too often that we're going to be interested in representing a line in polar, but there you have it, okay? We had talked about symmetry, and we've talked about the symmetry about the polar axes, which effectively is the x-axis, well, in which case you just replace theta with negative theta, and if the function rings true, such as a cosine function, as does here, then we have that function is in fact symmetric about the polar axes, or the x-axis, as we might want to think about it, okay? Then, of course, we also talk about the symmetry about the line, the radial line, theta equals pi over 2, and that's going to be, as we see here, okay, that's going to be true when any angle is replaced with its supplement of sorts. Okay, so if theta is the angle, and the supplement will be pi minus theta. So if a function, if we replace theta pi over 6 and theta 5 pi over 6, they are point symmetric about that line. Okay, in our functions, which are sine functions, okay, we can see by replacing theta with pi over 6, we get 2, and replacing theta with 5 pi over 6, its supplement, if you will, we get 2. So therefore, we're going to conclude that we do have symmetry about the polar axes with this function. Okay, and all these functions as listed down here, okay, just by virtue of the fact that they have a sine of theta, okay, would actually also possess that element of symmetry. Okay, they might possess additional elements of symmetry, but at least we know they possess this symmetry about the y-axis. Okay, symmetry about the pole is when we replace r with negative r. So 5 pi over 4 and negative 5 pi over 4 are symmetric about the pole. Okay, and 5 pi over 4 and negative 5 pi over 4, okay, would be symmetric about the pole. Of course, negative 5 pi over 4 would be the 5 pi over 4 projected backwards, okay, which would be equivalent to swinging this point 180 degrees around, and that's effectively what we mean by symmetry with respect to the pole, as you might think of as the origin, but of course that is the pole in polar coordinates. So they're basically 180 degrees apart. Replacing r with negative r, so r theta and negative r theta are point symmetric with respect to the pole. Okay, and so that is a discussion of this so far. And again, if r theta and negative r theta are on the same function, then it is symmetric with respect to pole. Okay, we will examine aspects of symmetry for particular functions in the forthcoming video. Okay, that'll do it for this.